In Chapter 19, we are going to be learning about what's called a confidence interval for proportions. Lots of new stuff, so make sure that you're taking notes, and if you don't understand something, make a note of it so you can ask in class. So a lab studies corals and the diseases that affect them. They sampled sea fans. Okay, this is a picture of a sea fan. They look like a tree, but they're actually a colony of genetically identical animals. So these are living, breathing things, but they do look tree-like. At 19 randomly selected reefs along the Yucatan Peninsula and diagnosed whether they were affected by the disease aspergillosis. You don't need to worry about the disease, it's just for the problem. In specimens collected at the Las Redes Reef, the scientists found that 54 of 104 sea fans sampled were infected with the disease. What can this study tell us about the prevalence of the disease among all sea fans? So our goal in this lesson is to discuss, what can we fully learn about what this small sample tells us about all sea fans. So we're going to dig deeper and we're going to answer some questions as we go. What do we know about the sampling distribution of the proportions of infected sea fans? So this is purely based on the sample. So we have some questions to answer. Is this a normal model? Can we use a normal model here? So of course, we have to check the same conditions that we've checked in the past. So let's take a look. If you remember, the first condition we always had to check was the random condition. And yes, we were told in the little blurb on the previous slide that they were randomly selected. Then we have to check the 10% condition. So we sampled 104 sea fans. So if you remember, when we're doing the 10%, we simply add a 0 at the end of that number. So there are definitely at least 1,040 sea fans in the world. They're all over the place on coral reefs. Then the next thing we have to check is the NP and NQ condition. So N was 104. To figure out P, we see out of the 104 that we sampled, 54 had the disease. So 54 out of 104 leaves us with 0.519. So there's our P. Our Q is simply taking 1 minus that answer, and so P is 0.519 and Q is 0.481. So now that we have our P and our Q, we can calculate our NP and our NQ. So NP 104 times 0.519 gives us 54, which is definitely bigger than 10. And NQ 104 times 0.481 gives us 50. And so both of those are bigger than 10, which means we've met all of our conditions. So yes, a normal model is appropriate here. So then the next question becomes, what is the mean for this normal model? And remember, the normal model represents the whole population. Is it 51.9% that we were just looking at? And the answer to that is no. The mean of all sea fans infected is not 51.9%. That was simply the mean for the sample we took. So we don't know the mean for all sea fans or the whole population. Well, what is the standard deviation? And can we find it? Because that's usually the next thing we find with the normal model. And the problem is we are not able to find the standard deviation. The reason we can't find the standard deviation is because if you remember, that formula looked like this. Standard deviation was the square root of P times Q divided by N. The problem is the P, the 51.9%, that's not P, that's technically P hat. And so we can't find the standard deviation because we don't actually know P. So what can we find then? Since we don't know P, we can't find the true standard deviation of the sampling distribution model. Instead, we will just use the sample proportion P hat to estimate the standard deviation instead. So we're going to estimate standard deviation. And because this is an estimation, we're not going to call it standard deviation. We're going to call it standard error. Very similar concept. Standard error is simply what is found when we estimate the standard deviation of a sampling distribution using statistics found from a sample instead of the population. So when we use a p hat and a q hat instead of a p and a q, we're finding standard error instead of standard deviation. However, their formulas look very, very similar. The formula for standard error looks just like this. Instead of standard deviation, SD, we use SE for standard error. And instead of P, we're using P hat. But if you notice, this formula looks exactly like the one I wrote down on the previous slide, except it has hats instead of regular P and Q. So it's found the same way, but it's an estimate, which is why we call it standard error instead of standard deviation. So we're going to go ahead and calculate this standard error. So let's calculate the standard error for our CFANs. So to do that, we need P hat and Q hat, which we already know. So the square root, P hat was 0.519 times, Q hat was 0.481 divided by, and the sample size n was 104. So if you round, and remember we always go with two non-zero digits, I end up with 0.049. So we're thinking about this like standard deviation, but it's called standard error. So let's take a look at what that means for our normal model. If you remember, when we first learned the normal model back in chapter 6, we knew that the mean was always in the middle. Well, here's the problem. We don't know the real mean. So all I'm going to put here in the dead center is P, because P represents the real mean, but we don't know it. Now, if you remember, these little marks represented standard deviations. Every time we went left or right 1, we went up or down a standard deviation. So 0.049 is the amount that we're going up or down. So I'm going to go to the right. So all I'm doing is to find this next little mark right here. I'm going to take P, which was the middle, and I'm going to add. Wow, that looks really bad. Let's try and erase that again. I'm going to take P, and I'm going to add 0.049. Well, to find the next little mark, we're going to add to what we just wrote another 0.049. So this mark is P plus, if I take 0.049 and I add another 0.049, I get 0.098. Then if I go one mark further, I'm going to add another 0.049, so I end up with P plus 0.147. Same thing works going the other direction, except we're going down. So to find this mark to the left, I'm going to take P and I'm going to subtract 0.049. To find the next one, I'm going to subtract another 0.049. So P minus 0.098. And to find the third one, I'm going to subtract another 0.049. So P minus 0.147. So this would have been the cutoffs for the normal model that we would have learned back in chapter 6. And if you remember, these little marks had specific percentages associated with them. If you remember, this first set of marks, that represented 68% of the data. The second set of marks, between those, represented 95% of the data. And then if you remember that third set going all the way out, if you remember, that represented 99.7% of the data, which we're going to be talking about in just a little bit. So what does all of this mean to us? So here's what we know. Because it's a normal model, about 68%, that was our first cutoff, of all samples of CFANs will have means P within 1 standard error of P. So P plus or minus 1 standard error represents 68% of our samples. 95%, there's those cutoffs, of all samples of CFANs will have means within 2 standard errors. So the mean plus or minus 2 standard errors will represent 95% of our CFANs. So, in other words, if I'm P hat, remember P hat is the sample mean. If I'm P hat, there's a 95% chance that P is no more than 2 standard errors away from me. Notice 95, 2 standard errors. That's exactly what we just looked at here. So if I'm P hat, if I'm the sample mean, then there's a 95% chance that the real P for all CFANs is no more than 2 standard errors away from me. So we will never know the true value of P. That's what comes with confidence intervals. We're never going to know the true P value for the whole population because it's impossible to sample and to study the whole population. The best we can do is create what's called an interval. So, I have some true or false questions. So first true or false question. 51.9% of all CFANs are infected. Well, the key word there was all. And so that makes this absolutely false. And the reason is the 51.9% that were infected, those were samples. So we can never guarantee that the sample truly reflects the population. Okay, well, it's probably true that 51.9% of all CFANs are infected. The problem is, again, that 51.9% is about our sample. It doesn't matter how much you want to say it relates to the population. It's not ever able to go straight to the population from the sample. So again, this is false. So let's look at 3. 3 is slightly different. We don't know exactly what proportion of CFANs are infected, but we know that it's within the interval. Here's the mean, 51.9%. We're going to add and subtract 2 standard errors, so 2 times 4.9%. Well, if we take 51.9 and we subtract 2 times 4.9, we get 42.1. If we take 51.9% and we add 2 times 4.9, we get 61.7%. So we don't know what proportion of CFANs are infected, but we know that it's within that interval. Well, here's the problem. This is really getting close to what we want, but the problem is we can't say definitively that our answer is between those numbers. We can never say for certain because, again, all of this is based upon estimates. So we're not for certain that it's in that interval, but this is getting much closer to a true statement than the other two. So let's look at one last true or false statement. We are 95% confident that between 42.1% and 61.7% of the CFANs are infected. This is finally a true statement. We are not saying we are 100% confident. We are not 100% certain, but rather we're only 95% certain about our interval. That's the key important factor here. We're not saying 100%, we're saying 95% because 95% refers back to that 2 standard errors. And so because we used 2 times the 4.9%, That right there is 2 standard errors. That's why we said 95%. So, what do we call this statement that we just made? This statement is called a confidence interval, which is what this entire chapter is about. It's about confidence intervals and estimating the real proportion based on a sample. So let's take a look at what this means. So what does 95% confident mean? It means that we are 95% confident that the true proportion lies within our interval. We're not 100% confident. We're only 95% confident that our proportion lies within our interval. So what that also means, because we're only 95% confident, it means that it is possible that our sample is one of the 5% that failed to produce an interval containing the true proportion. Every time we take a new sample, each new sample is going to have a slightly different, that should be p hat. So we'll also produce a new interval. So looking at this picture, this kind of gives you a visual. Okay, this green line that you see going through the middle, that represents the real proportion. That represents p. We're just making it up, but that represents p. So I want to point out a few of your intervals. This first one right here, and this one right here, and this one right here. Do you notice that the first two are completely above the green line, and the third one is completely below the green line? Notice the green line doesn't go through them. What that means is that p, our real proportion, isn't in those intervals. Those are the 5% that don't produce an interval that works. That's why we are never able to say 100% confidence, because we can never guarantee that every possible interval works. So those 3 did not work. The rest of them, some of them, like this one right here, let me change colors. This one right here, it was very, very close to the red dot, and the red dot is p hat. So was this one. Whereas some of them, we barely made the right answer. Like this one right here. That one, as you can see, it's on the very far edge. So is this one right here. So some of them are barely going to catch the p-value. Others of them are going to have it very close to the middle. But we don't know that because we never actually know p. This is just a visual to help you understand where these intervals are going to fall to help you out. So now the next question becomes, how do we actually calculate these confidence intervals? So we have some steps to go through. First step, you have to determine if your conditions are met. Same 3 conditions as always. Random, 10%, but now we call it NP hat and NQ hat. Then calculate the standard error. And if you don't remember, that's the NP, I'm sorry, not N, let me get that formula right. That is P hat, Q hat, divided by N. Then determine how many standard errors to use based on what confidence interval you want. Each question is going to give you a percentage. If it gives you, and for our sake, we only have 3 options. If it gives you 68%, you're going to use 1 standard error. If it gives you 95%, you're going to use 2 standard errors. And if it gives you 99.7%, you're going to use 3 standard errors. That's based on your model that we learned way back in chapter 6. So for today, those are your 3 numbers that you're going to use. Once you've found those 3 numbers, then you simply calculate your interval. So let's look at how all this works. So A January 2007 Consumer Reports study found that about 15% of the 525 broiler chickens tested were infected with salmonella. Are the conditions for creating a confidence interval satisfied? So, what are our conditions again? Well, the first one is random. We are going to go ahead, even though it doesn't say the word random in the problem above, Consumer Reports is a very reputable magazine, so we're going to go ahead and assume that random is safe to assume. Then we got the 10%. Take our sample, 525, add a 0. Do you think there is at least that many broiler chickens in the world? Yes, there is definitely. It is safe to assume that there are 5,250 broiler chickens in the world. What's the other piece? We got to check NP hat and NQ hat. Well, 15% did have salmonella, so that's your NP hat. So 525 times 0.15, which I end up with 78.75, which is bigger than 10. NQ hat would be 525 times 100, take away 15% is 85%, and I get 446.25. So I feel like all the conditions are met, so we're good to go. Next step. Now that we've found our conditions, the next step is to find your standard error. So we need to take 0.15 times 0.85, which were our P and our Q, divided by 525. Pick up your calculator. Remember, we want two non-zero digits. I get 0.016. So then the next question becomes, how many standard errors did we want? Well, the key number here is a 95% confidence interval. So 95 always means 2 standard errors. So I need 2 standard errors, which means I need 2 times 0.016, which comes out to be 0.032. So that's our magic number. So to find our interval, all we have to do is take our P hat, which is 0.15, and add and subtract 0.032. And when we write our interval, we're just going to write it in parentheses with our low number on this side and our high number on that side. So if I take 0.15 and I subtract 0.032, I get 0.118. And if I take 0.15 and I add 0.032, I get 0.182. So what does our confidence interval say about chickens sold in the United States? This is going to be kind of your blanket statement that you're going to make. So it's always going to start off with, we are, and you're going to have to list your percentage. So in this case, 95% confident that the true proportion of, in this case, infected chickens is between, so we set our percentage, we mentioned the true proportion, and then the infected chickens, and now we're going to use our percentages from our interval, is between 11.8% and 18.2%. So the things that you're going to change on this statement from question to question, that percentage is always based upon what was asked in the question. You're always going to say confident that the true proportion of this is going to change from problem to problem. And then so are your two percentages. So those three things are basically fill in the blanks. The rest of it is the same sentence over and over again. And so you just made your first confidence interval. Let's look at another problem. A May 2007 Gallup poll found that only 11% of a random sample of 1,003 adults approve of attempts to clone a human. Construct a 99.7% confidence interval for the percentage of Americans who approve of cloning. So the first thing we need to do, because this doesn't break it down in steps, we have to break it down ourselves, is to check our conditions. So your first condition, was our sample selected randomly? It says right here, random sample, so that's definitely good. 10%. So if we take our sample of 1,003 and add a 0, do you think there is at least 10,030 adults in the world? I would say that's a safe assumption. And then NP hat and NQ hat. So we're going to take 1,003 times our P was 11%. That gives us 110.33. And then 1,003 times, well, 100 minus 11 is 0.89. And so if you multiply those, I get 892.67. Either way, both are bigger than 10. We're ready to move on to our real steps. So that was the conditions part of it. So now to calculate our interval, that we first need to find our standard error. So big square root, P hat is 0.11, Q hat is 0.89, divided by 1,003. So what decimal do you get? Mine rounds to 0.010, so 0.010. So then the question becomes, how many standard errors do we want? Well, our magic number was 99.7, and if you remember, 99.7 was 3 standard errors. So we need 3 of these 0.010s, which is 0.030. So that's our magic number. So we're going to take our P hat 0.11 and we're going to add and subtract 0.030, which gives us, if you take 0.11 and you subtract 0.030, you get 0.08. And if you take 0.11 and you add 0.030, you get 0.14. So there's our interval, but now we have to have that conclusion statement. So remember, it always starts off with, we are. Now what's our percentage this time? 99.7% confident that the true proportion of, and here's the next fill in the blank, we're looking at Americans who approve of cloning, the true proportion of Americans who, I can't fit it there, hang on, who approve of cloning is between, and here's our other fill in the blanks, 8% and 14%. So that's that 3-piece fill in the blank. The percentage, what the true proportion is that we're talking about for this problem, and your percentages. Okay, so let's look at one last example and then we are done. First USA, a major credit card company, is planning a new offer for their current cardholders. The offer will give double miles on purchases for the next 6 months if the cardholder goes online and registers for the offer. To test the effectiveness of the campaign, First USA recently sent out offers to a random sample of 50,000 cardholders. Of those, 1,184 registered, giving 95% confidence interval for the true proportion of those cardholders. So we have got some work to do here. So the first thing we need to do is check our conditions. So what's our first condition? It's always random. So random, and there's the word random. We're good to go. 10%. Well, 50,000, tack on another zero, we're at 500,000. Do you think there's 500,000 credit card holders out there? I would probably say so. So we're going to say that is a safe assumption, is that there are 500,000 card holders out there. Here's the problem. We don't know p hat yet. We have to calculate p hat before we can calculate in p hat. So we had 50,000 card holders, 1,184 of those 50,000 registered. So if you take 1,184 divided by 50,000, I get 0.024. So there's our p hat. So now we can calculate NP hat and NQ hat. So we're going to take 50,000 times 0.024, and I end up with 1,200. And we're going to take 50,000 times, if you take 100 minus 2.4, or 1 minus 0.024, you get 0.976, which gives us 48,800. Either way, both of those are bigger than 10, so we can move on to finding our standard error. So that was the first piece of the puzzle. Those are our conditions. Standard error. Big square root. P was 0.024, Q was 0.976, and N was 50,000. Now, when I put this in the calculator, I get 3 zeros to start it. So this is going to be a really tiny number. So it's okay if you only use one more digit. So 0.0007. Well, now the next question is, how many standard errors do we need? Well, the magic number was 95%, which is 2 standard errors. So 2 times 0.0007 gives us 0.0014. So then we need to take p hat, which was 0.024. We need to add and subtract our 0.0014. So let's see what interval that leaves us. So in your calculator, 0.024 minus 0.0014, I get 0.0226. And if you take 0.024 and you add 0.0014, I get 0.0254. So, we have a different question here than our typical conclusion sentence. If the acceptance rate is only 2% or less, so that's their normal acceptance rate, is only 2% or lower, the campaign won't be worth the expense. Given our interval, what do we have to say? Well, 2% is 0.02. Look at our interval. Our interval is bigger than that. So if it's 2% or less, the campaign is not worth the money. Well, 2% is below our interval. And so because of that, that's a good thing. Our interval is higher, which means it's worth the money. So our interval is higher than 2%. So it's worth the money. And that's the end of today's lesson, and that's the end of the first part of confidence intervals, and we'll see you in class.